All right, let's start chapter 15 today. Just a quick note, I'm at my cabin in the woods today, so I'm recording outside, out the screen porch, so hopefully the sound of rain and birds will not be too distracting, but it is quite relaxing here. Okay, chapter 15. We're going to look at processing sequences and how time series or sequences data that comes in over time um, and is often variable length data. So like words, sentences, stock prices, that sort of stuff. How we process these sequences or time series, as they're often called. And we're going to use something called recursive neural networks for this. We're going to rely much of this on our book. Again, chapter 15 of the text, but I'm also going to pull in some material from Jeff Heaton's course from the Washington University in St. Louis on this recurrent neural networks too. So um, so as before, we set up our libraries here, and then we're going to get into processing neural networks. The first section isn't going to come from the textbook, but the first two sections, but is from Jeff Heaton stuff. And it's just another explanation of recurrent neural networks. So again, the textbook goes over recurrent neural networks and talks about them, shows different descriptions of these networks and how they're set up. But there's a fair amount of math in his descriptions here, and I find that might not be the best for some students to understand about training these and setting these up. And so this is from Jeff Heaton's original notebook on these, and just kind of talks about these and has some diagrams. So I think this is a good explanation of recurrent neural networks. Basically, recurrent neural networks, you have a you have some inputs often going to a hidden layer, and that's going again to some outputs, although there might be multiple hidden layers. But the hidden layers are recurrent in that they get inputs not just from the input layer, but also from themselves. Each unit feeds back on itself. So each unit can look at its activation and the time update before, as well as the inputs, new inputs coming in. How this is often done is that at the end of when we put some inputs there, we update the hidden units, and then update the outputs. We then make a copy of all the hidden units in what are often called context units. So these context units are just copies of the activations, the hidden units, and then those are used to feed into the hidden units. So basically, the hidden unit just sees this a copy of themselves, so they can kind of understand over time how they've changed. So that's why they're called recurrent neural networks, is because the idea is that there's a recurrent connection from each of these hidden units back into these hidden units again. So, so I want you just to read through this and see if you can answer these questions about recurrent neural networks. Once we have these, when we can feed sequences into these networks, we can feed data into these networks, and like when we do an image, we provide an image all at once. But here we can, with like a sentence or words or music, we can provide a single word or a single character at a time, and then another character and another character, and then we can handle variable length inputs into here. So because we don't know how long time series are, and then we can also look for patterns in time for this. So that's the idea of these recurrent neural networks. Then we're going to go through this simple recurrent neural network again. This is again something from Hinton's work here. That we're going to look at, and we're going to provide some simple inputs to this neural network here. So these are our inputs, and the idea is that maybe we have a person looking out their window, and they just see cars driving by. Maybe they're on a little cul-de-sac, and there's only 4 neighbors that live down this cul-de-sac, and they just watch, and all they see from their couch is that they see car 3 drive by their window. So first there's no cars driving by their window, and then car 3 drives by their window, and then there's no cars, and then later car 1 drives by their window for this. And then we ask just a real basic question. If we see a sequence of cars driving by here, what was the last car we saw? So if we saw car 2, car 1, and then no cars for a while, then we ask them, what was the last car you saw? And then it should say, oh, I saw car 1 last. So the output of this should be car 1. So we set up this network here to be trained. And it trains relatively quickly. It's just a simple neural network here. So now rather than when we used to do these networks, we'd always use like dense layers for simple neural networks or convolutional layers. Now we'll use simple recursive neural network layers. These are traditional versions, so this is that. We'll also look at more advanced versions. One will be called long short-term memory, and the other one will be GRU, gated recurrent units, I think it's the acronym, in here. So, and a network is, again, relatively simple. It's just one layer, or that takes the input here. And again, our input is just fed into this. So our input's going to be 14 sequences, and each sequence is going to be 6 objects long. And so we're actually using fixed length sequences here, although we could use these for variable length sequences. And then we just one input here. And we have an output. We predict there's 4 types of cars or objects, and we just want to predict the last one. So our output is one of 4 classifications for this. So again, we set up this network sequentially, we compile it, and we train it with our fit function as normal. It trains over time, and then we predict the accuracy of this. So here's our results here. So here's the what we predicted, and here's what we expected. So we expected the cars, like the last car, to be like 0 or 1 or 2, and in most cases it did correctly. There are a couple places that it does goof up here for it. But this is just a way of classifying time sequences and feed them into the network for this. Okay, so now in section 3, we're actually going to jump back into the textbook and forecasting time sequences here. So we're going to start looking at this section on forecasting time series or sequences. And so we're going to generate some random time sequence here. This almost looks like maybe a stock market price or sunspot data or something like that. And so we're going to write a little function to do that, to create these random sequences. And we're going to break it up into parts. So we can have some for training and some for testing here. And we're going to try out some simple things. So so let's set that up. So we set up our data, we generate our time sequences with this function, and here's a plot of a couple sample time sequences that they're somewhat randomly generated from 2 different sine functions over time. So now we're going to look at some basic examples of like what we could compare against. So one of the obvious ways, like if you're trying to predict the weather, you say, well, if it's sunny and 60 degrees today, a good prediction tomorrow is maybe sunny and 60 degrees, and the next day maybe the same as the day before. So you can always predict exactly what you have. So if you are at this point, you can predict that same point the next day, and you're often going to be close to what. So our first baseline prediction here is just predicting what the last value was for this. So in this model, at each time unit, our prediction is going to be the input one value less than the current than we're looking again. So if you're looking at the prediction for tomorrow, that's going to be the value from today or this unit. So, and this is just some short cuts that kind of do that for us. And we're going to look at for a whole series of predictions, how far each prediction is from where it was supposed to be. And so we're going to look at the average error over these. We're actually going to look at the average square of these errors because, again, the error might be positive or negative. So we'll look at this mean square error. I don't know if you remember, but way back in one of the first units, we talked about this either root mean squared error or mean squared error as a way of measuring this error, and that's what we use. And so we want to keep this error small. So we see that the mean square error is almost 0.02 here. So it does actually a relatively good job at predicting this. Another baseline metric is to say, well, let's just take the last couple inputs and flatten them out. Just look at the last so many inputs and feed them into a normal network with a simple unit here. And so this is another baseline unit. And again, that we'll train that, set that up. And that has again, a relatively smart error how it predicts versus where the actual next value is shown here. So like I say, in the textbook, they go over these baseline metrics here, and then they talk about implementing a simple RNN and setting that up. So that's our next phase here, is to see if we can implement this with a simple RNN. So the simplest RNN just has a single node. We feed in one input at a time, and we have one node there, and it's a recursive node, so it knows what it's seeing. It's a very simple neural network, trains very fast, but it's not the most accurate in the world. Now, one thing you will see, this I said it trains so fast, but you're saying, well, it seems like it's kind of still training. It's kind of slow. That's because, again, to train this network, we have to do lots of updates. So if we're feeding a sequence of 50 nodes or 50 numbers into the sequence, we have to feed it in there and then have it predict the next value. And then to do the next value, we have to back up and feed in the previous 50 values into it and then have it predict the next one. So there's lots of updates to this network. And again, we have a mean squared error of 0.1 here, and it's doing okay, but it's not great. But again, that kind of network is not doing a lot. And so often we want to do be able to monitor kind of changes over time. One of the things is that with these time sequences, we want to see patterns. We want to see these larger dips going up and down, and maybe even smaller dips in here also. And so you'll need more, nodes to kind of keep track of these historic trends. So here we've got a simple neural network with 20 units fed into another layer with 20 units, and the output is 1. So we're inputting 1 unit at a time, and we're outputting 1 unit at a time as we go through here. And so we'll see. So basically, we're feeding the network each of these data points values over time. So it's each of these values feeds it in. And then at the end, it says, okay, now we're getting here. Where would you predict the next value to be? And it would predict some value, and then this is what the actual value is for this. So here's again, training's going to take a little while, so I'm just going to let this training run. So again, now with this network done, we have a very low mean square. It's getting very good at predicting where the next value is. So these recurrent neural networks often can learn these time sequences and learn to predict what the next value is here. Now, if you're thinking, oh, I can predict what the next temperature is in an hour from now, can I predict what it is in a day from now or in 7 days from now? How far ahead can I look, and how does that work? So now we're going to look at forecasting a number of steps ahead of time for this. So what we're going to do here is we're going to have the network predict what the next value is, and then we're going to add that prediction into our sequence. So we have our sequence here and we're predicting here, and then we're going to predict one more day ahead or one more time slot ahead. And then we're going to add that to our sequence and have it predict again. So it's going to keep predicting ahead again and again for this. And so that's what this is looking at, a number of days ahead. And again, there's a lot of Python code in here where we're actually we're predicting one value ahead here. Using our model, we're predicting that. And then we're concatenating that onto our time sequence. So we're using X as our time sequences. We're adding this new prediction onto our time sequence. So now we have a longer sequence here, and then we're going to do that again. We're going to, in this case, we're going to do it 10 times. We're going to predict something and add it to our time sequence, and then we're going to retrain or rerun our model to predict with this new extended input what the next sequence is. So here's kind of the idea. Here's our time series, and this is the red are the actual ones, and the X is the forecasted values for it. So you can see it is doing an interesting thing. It is thinking it should, it's looking at this history, and it's seeing it's going up and then down again, and is going to try to predict that for this. So it is learning that. So again, do your write-up about these recurrent neural networks and how this how they generally work. Now, one of the challenges with recurrent neural networks, let me just jump through the textbook here. Okay, yeah, we're doing deep networks and forecasting multiple times ahead here. Okay. So one of the problems with some of these recurrent neural networks is that for very long time frames, we often lose information. We focus too much on recent changes to the data and don't see long-term changes. This is particularly important with language where you might have a noun at the very beginning of a long sentence, and then towards the end of the sentence, you want to refer back to that noun with a pronoun, and you might need to know the gender of that noun and things like that. But it was a long time before, you might have forgotten, your network might forget what that value is. So there's been some development of more advanced cells or nodes for this, and one is that's commonly used is called long short-term memory. So this was proposed back in the 90s, but has seen a resurgence in recent years for this. And the idea of a long short-term memory is that it holds some state in memory and only changes it at time for it. So again, similar to recurrent neural networks, you're feeding some input into that, but rather than just having its old state put back in there, we have two recurrent connections, a context and a change variable that's input. So it's kind of showing this getting this is at one time, and this is the future at the current time. So at the current time, we see the input, but we also get two values from the past update of this long short-term memory network or node for this. Again, these networks are a little complicated here. They have a number of different functions in them that are computing things. But one thing just to So, like recurrent networks, we always send some output out, and that output is sent back and recurred. So we always see the output of the unit from last time. But there's also this context. This context is some value, internal state of this node. And there are a couple gates in here that decide when to change the context here. And so there's a forget gate that controls if the context should be forgotten, and then another one that should be where we should remember the context. So we should remember some value. So again, if we see some value, a new value come in, we want to remember that for that. So these networks are a little more complicated. Again, you don't have to understand all the internal functions, but just remember that they hold more context in them than a traditional value. So so we're going to set up this network again, but again, we're going to use these long short-term memory networks here, LSTMs, for this training rather than the simple recurrent neural network. So when you're in Keras, you'll see, let's see, where is our network here? When you're working with the old school simple recurrent neural network node, it is called a simple RNN layer. And then when we're working with a LSTM node, the layer is just called LSTM here for this. And so here we're getting feed into an LSTM layer to remember some sequences and then feed that in and another LSTM. And so maybe the goal is that the second LSTM, maybe we'll see some even longer term patterns in this data for this. And again, this is going to take a while to train. And we can see we get, here we have both our training data and our validation data. And again, we're getting some nice low errors for this. And if we plot this out, if we have it generate a number of sequences ahead of time, we can see it does a pretty good job of generating or forecasting what the next value is for this. So just, this graph is only is showing a sequence of predictions, but again, we're not asking the network to predict multiple days or time slots ahead. This is just if we know all the data up to this point, can you predict the next value for this? So, now, because LSTMs, long short-term memory networks, are rather complicated, they've developed a simplified version of this, just called gated recurrent units. And those have been shown to run very well also, even though they're much more simpler. They just hold state information a little better, but not in such a complicated fashion. So we can actually run this, train this network with these gated response networks also. So we look at our text, again, we're talking about handling these long sequences, and again, we often, because of gradient problems, we'd lose some of this data over time here. And the textbook talks about some normalization stuff, but then, which again is just is not used that much these days. Instead, we see these LSTM cells here, and how to set those up, and then it walks through again how they work, but again, the internals of these are not that important. And then again, and then there's another version of this with people cells. Those aren't that important now, but then these gated recurrent units were also proposed in 2014 and are used frequently today also. And they're again a much simpler version of these values. And so there are, while there's only one value that's going out rather than two with long short-term memories, that value isn't just the last value here. It's a state value which combines the current input with the current state of this network, of this node. So, and again, these training of these networks, because again, we're sending these sequences through them and doing lots of updates over time. So even though these are relatively small networks, they do take a lot of time to train again, because what generally happens is that we have, if we're predicting the next cell, we might we'll send these time series, and we're actually regenerate like 10,000 time series, and we're sending 7,000 through. But each time, what we're doing is we're sending this whole time series, all these updates we have to update many times, and then have it predict the next one, and then look at a new time series and have it predict the next one. So the updates do take a while to run. And then again, with these units, we can use that to predict forecast the time series over change. That's the basic thing. The textbook then goes into some using these stacked 1D convolutional layers. We're not going to go over this relatively new stuff, and so I'm going to skip over this whole section, this last part of the text using CNNs to predict stuff. We'll look at some other stuff related to CNNs in the next unit, and predicting images and things like that, which I think is a little more interesting. So that wraps up chapter 15.